Hi, in this screencast I'm going to walk you through the problems in project 1 and give you some hints along the way on how to solve those problems. This project is about writing PicoBot and HMMM programs. So here's the PDF for the project. You can find a link to this PDF on the assignments page of the course website, and on that page you will also see a link to the zip file for the project. And when you download and extract that zip file in your computer, you will see a folder such as this containing all these files. Alright, now some of the files that you have in that folder are the starter files for the problems in the project, and then you have a file called report.txt, which is a template for you to use when you write your report for the project. And then there is this file called runtest.py that you should use to test if your solutions meet the input and output specifications. Alright, so now let's walk through the problems in the project. So the first problem is to write a PicoBot program called empty_room.pb with rules that instruct the PicoBot to cover an empty rectangular room. Okay, now your program should work regardless of how big the room is and regardless of where the PicoBot starts, meaning your program shouldn't assume anything about the dimensions of the room or the initial position of the PicoBot. Alright, now for this problem you want to use the starter file called empty_room.pb to write your PicoBot rules. Okay, now one way to solve this problem is to write a set of rules that takes the PicoBot from its initial position to one of the four corners of the room and then covers the environment. So it's a lot easier to cover a rectangular room when the PicoBot starts in one of the four corners. Okay, so that's one way to solve this problem. Now once you have written your program, you should test it, and you can do that by running this command on the terminal. And when you do that, you will see several messages printed on the screen, and if your program is correct, at the end you ought to see the message that says coverage reached. Okay, so that's problem 1. Now in problem 2, you want to write an HMMM program called squared_distance.hmmm that takes 4 numbers as input. So let's call these numbers x1, y1, x2, y2, and these numbers, they represent the coordinates of 2 points on a plane. Okay, now what the program is supposed to do is print the squared Euclidean distance between the 2 points, and that is simply given by this formula that you see here. Okay, now for this program you want to use the starter file called squared_distance.hmmm, and when you open that you'll see that the program is organized in this 2-part manner. Okay, and this is going to be true about all the HMMM programs that we are going to write in this project. So you'll see a main part, and you'll also see a function part. Now in the main part you typically read inputs from the user into some registers, and then you call a function that calculates something in some register, and then the main part prints the value of that register as the output, and then finally halts the program. Okay, and then the function part implements a set of instructions that read that get the inputs from some registers and then compute something into some output register and then transfers control back to the main part. Okay, so that's how all of our HMMM programs are going to be organized. Now in this program, the main part is supposed to read x1, y1, x2, y2 into some registers and then call this function that calculates the squared Euclidean distance using this formula into some register, and then the main part is supposed to print that register and halt. And then in the function part you want to implement a set of instructions that actually calculates the squared Euclidean distance and transfers control back to the main part. Okay, now once you have written up your program, you first ought to assemble it. So you want to turn squared_distance.hmmm to squared_distance.b, and you do that by using the hmmm assembler.py program. Okay, now once you have assembled your program, you can run it using this command on the terminal, and when you do that, the program will wait for 4 inputs. So if we type these as the inputs for x1, y1, x2, y2, and if your program is correct, then it ought to print the value 25, which is indeed the squared Euclidean distance between the points 3, 2 and -1, 5. Okay, Now, in all the HMMM programs that you write, try and reuse registers as much as possible. Okay, so just keep that in mind. Okay, so now let's move on to the next problem, which is called sum of ints. So here you're supposed to write a program called sum of ints.hmmm that takes a non-negative integer n as input and prints the sum 1 plus 2 plus 3 and so on all the way up to n. Okay, so for example, if n is 5, the program is supposed to print the sum 1 plus 2 plus 3 plus 4 plus 5, which is 15. Okay. Now for this program you want to use the starter file that is called sumofints.hmmm, and here again you have the main part and the function part. In the main part you want to read the number n into some register and then call this function that calculates the sum into some register. Then the main part prints the value of that register and hearts. In the function part you want to implement a set of instructions that gets the value of n from some register and then computes the sum into some register and then transfers control back to the main part. Okay, so that's what you want to do here. So now what I'll do is I'll give you some hints on how you may want to organize your code in this function here. Okay, so let's do that. So I'm going to say that the function is going to expect the input n in register R1 and that it's going to place the result, which is simply 1 plus 2 plus 3 and so on all the way up to n in R2. Okay, so here's an outline on what you may want to try and do for this problem. Okay, so you first need to set R2 to the value 0. Okay, and then what you do is you check if R1 is greater than 0, and there are two answers to this question, right? So if it is yes, then what you want to do is you want to add R1 to the value of R2. Okay, and then what you want to do is you want to decrement R1 by 1, and then you should jump to the location given by this placeholder a. Okay, and where is that location in this function? Well, it's going to be this guy here. So whatever the instruction number of this guy is, that's where you want to jump. Okay, so that's what you do. So these are the things that you do when R1 is greater than 0. Now what if R1 is not greater than 0, meaning it is less than or equal to 0? Okay, in that case what do you do? Well, you simply jump to the caller. Okay, and the way you do that is by jumping to the address that is given in R14. Okay, all right, so that's sort of like an outline on how to go about solving this problem. So let's look at an example, a concrete example. So let's say the register R4 contains the value 3. Okay, meaning n is 3. Then we start R2 with 0. Now R1 is greater than 0, so we simply add its value to R2. So R2 is now 3, and then we decrement R1 by 1, so that's 2 now, and then we jump back to this location and we check if R1 is greater than 0, and it is. So what we do is we simply add it to R2, so R2 is now 5, and then we decrement R1 by 1, and then we jump to this location again and test if R1 is greater than 0. Well, it is, so we simply add it to R2 and then decrement R1 by 1, so this is now 0, and then we jump to this location, but now R1 is 0, so we are here. So in that case what we do is we simply jump to the caller. Okay, and when we do that, R2 contains the value 6, and that is exactly what we want, because that is 1 plus 2 plus 3. Okay, so this is one way to go about solving this problem. All right, now once you have written up your code, you should first assemble it. Okay, so you want to first turn this into a .b file, and once you have that, you can run it using this command on the terminal. And when you run the command, you need to provide an input. So let's say we type 100 for n. So now if your program is correct, then it ought to produce the result 5050. Okay, because that is the sum 1 plus 2 plus 3 and so on, all the way up to 100. Okay, so so that's problem 3. So now let's move on to the next problem, which is called primality testing. Okay, so here you want to write an HMMM program called primality.hmmm that takes an integer n greater than 2 as input and prints 1 if n is prime and 0 if n is not prime. Okay, now recall that a number n is prime if it is not divisible by any number in the range 2 through square root of n. Okay, so if you find any number here in this range that evenly divides n, then n is not a prime number. But if you don't manage to find any such number, then that divides n, then you conclude that n is a prime number. Okay, so that's the logic that you want to try and implement in this program. So here the starter file that you want to use is primality.hmmm, and that is again organized in this two-part fashion. So here you're going to read the number n into some register, and then you'll call this function that determines whether or not that number is prime and places the result 1 or 0 in some register. The main part will then print the value of that register in hot. Now the function is supposed to implement a set of instructions that figures out if the input n is prime or not, and it's supposed to place the result 1 or 0 in some register and return control to the main part. Okay, so here again let me give you some guidelines on how you may want to organize your function. Okay, so let's go back to this window, and here I'm going to assume that the value n is in R1, and that the function is going to place the result, which is either 1 or 0, in R2. Okay, now I'm going to need another register. Let me use R3 for the value of I. Okay, now I, remember, is going to be numbers from 2 all the way up to square root of n. Okay, so here's how you may want to organize the code. So we'll first store the value 2 in R3. So we start I at 2, and then what you want to do is we want to check if R3 is less than or equal to square root of n. Okay, I'm going to put an asterisk here, and I'll come back to this in a bit on how you want to think about this expression. Okay, so so we want to check if R3 is less than or equal to square root of n, meaning R3 is in this range. So here there are two answers, right? So there is a yes and a no. So when if this is true, then what you want to do is you want to check, is R1 divisible by R3. Okay, so you want to test if R3 evenly divides into R1. So remember that R1 contains the value of n. So here again you have two answers, a yes and a no. So what if this is true? Well, if this is true, then you know that n is not a prime number, because you have found a number that evenly divides into n, right? So in this case what you do is you store the value 0 in R2, okay, meaning n not prime, and then what you do is you jump to the caller, the main part. Okay. But what if R1 is not divisible by R3? Okay. In that case, what you need to do is you need to increment R3 by 1. Okay, so you want to try the next value for I. Okay, and then you simply jump to the location that's given by this placeholder A. That's this guy here. Okay, so you do this whole thing all over again. That's what we're saying here. All right. Okay, so now what if the answer to this question was a no, meaning R3 is now strictly greater than square root of n. Okay. Well, what that means is that we have looked at all the values from this range, right? And we have not managed to find a single number that evenly divides into R1, which is n, right? So in that case, what we do is we store the value 1 in R2, meaning n is prime, and we jump to caller. Okay, so that's the idea. So this is the logic that you want to use to test if a number n is prime or not. Okay, so now I'm going to go back to this asterisk here. Okay, so so there is a small catch here. So in HMMM you don't have the square root operation. All right, so how do we implement this expression in HMMM? So it's fairly straightforward. What you need to realize is that the expression R3 less than or equal to square root of n is absolutely equivalent to saying R3 square is less than or equal to n. I'm just squaring both sides. Now this is absolutely equivalent to saying R3 times R3 is less than or equal to n, and this is identical to saying R3 times R3 minus n is less than or equal to 0. Okay, now this is something that you cannot implement in HMMM because you just don't have an instruction for calculating the square root of a number, but this is something that you can implement in HMMM because you have instructions for multiplication, you have instruction for subtraction, and you also have an instruction for comparing an expression against 0. Okay, so this is how you want to look at this part. All right. Okay, so that's that. Now once you have written up your code for the problem, you again want to first assemble it into primality.b, and then you can run it using this command on the terminal, and then you type an input. So let's say n is 31, and then the program is supposed to print 1 because 31 is a prime number. Okay, and if you run the program with input n equals 35, the program is supposed to print 0 because 35 is not a prime number. Okay, so that's problem 4. Let's move on to the next problem, which is where you want to write a program called gcd_iter.hmmm that takes two non-negative integers x and y as input and prints their greatest common divisor. Okay, now the greatest common divisor of two numbers, we all know, is the largest number that evenly divides both x and y. Okay, and we're going to calculate the greatest common divisor of x and y using a very famous algorithm called Euclid's algorithm. Okay, so the idea is very simple. What the algorithm says is that if y evenly divides x, then the GCD of x and y is simply y. Okay, otherwise the GCD of x and y is the same as the GCD of y and x mod y. Now x mod y is nothing but the remainder of x and y. It's the remainder that you get when you divide x by y. Okay, so this is the algorithm that you want to use to figure out the GCD of two numbers x and y. All right, so here the starter file is called gcd_iter. So it's right there. Again, it has a two-part syntax. In the main part, you want to read x and y in some registers and then call this function here that calculates the GCD of x and y into some register, and then the main part will print that register as the result and halt the program. And in here, you want to implement Euclid's algorithm. Okay, so let me give you some hints on how you want to do this. So I'm going to go back to this window, and let's start with a new page. So here I'm going to assume that the input x is in register R1, y is in R2, and that the result, the GCD of xy, is going to be stored in R3. Okay. So here is sort of an outline for this function. So okay, so that's going to be some instruction number, so it's a placeholder. So you first check if R1 divisible by R2. So is R1 divisible by R2? So there are two answers. If yes, then what we do is we simply place the value of R2 in the result register, because R2, which contains y, is the GCD of x and y. Okay, and what you do is you jump to the column. Okay, but if R1 is not divisible by R2, then what does the algorithm say? Well, it says now the GCD of x and y is simply the GCD of a y and x mod y, right? So now what we're going to do is we're going to set R1 to the value of R2, and then R2 is simply going to be R1 mod R2. Okay, now here again I'm going to put an asterisk, and I'll come back to this in a bit. All right, and then once you have done this, you need to simply jump to the location A. Okay, and you need to repeat this process. All right, so all that we are saying here is that if x is not divisible by y, then the GCD of x and y is simply the GCD of y and x mod y. Right? So that's what we're saying here. Okay. So now let's take an example. Okay. So let's say that R1 contains the value 4 and R2 contains the value 6. Okay, then we have R3 here. Now, so remember that this is x and this is y. So is x evenly divisible by y? No, it's not. So what we do in that case is, according to this recipe, R1 is assigned the value 6, and R2 is assigned the value R1 mod R2, meaning the remainder of x and y, which is simply 4. Okay, and then we repeat the process. So now, does R2 evenly divide 6? It does not. So R1 is now going to be 4, and R2 is going to be R1 mod R2, or the remainder of 6 and 4, which is simply 2. But now we realize that R2 evenly divides R1. So we are here, right? So in that case, what we do is we simply set R3 to the value of R2, and we jump to the caller with this value in R3, and that is indeed the GCD of 4 and 6. Okay, so that's how this algorithm is going to work. Now I have to say something about this asterisk that I have here. Okay, now when we make this assignment, right, so when we want R1 to be the value of R2, and R2 to be the value of R1 mod R2. We cannot do it like this because when you refer to R2, R1 here, it's not the original value of R1, because R1 just has taken on a new value because of this assignment. Okay, so the way you want to do this is using a temporary register. So let's use R4 for that purpose. All right, so the way to do this is by saying R4 is the value of R1. So you remember R1 in some temporary register, and then you say R2 is R1 is the value of R2, and R2 is not R1 mod R2 because that's changed, but it's the original value, which is now in R4. So this will be R4 mod R2. Okay, so that's how you need to do this. Okay, all right. Once you're done implementing your program, you need to again assemble it. So turn this into a .b file, and once you have that, you can run it as follows using this command on the terminal. The program then waits for two inputs, so x and y, and if x and y are 54 and 24, the program is supposed to print 6, which is the GCD of the two numbers. And if you run the program with inputs 22 and 45, it's supposed to print 1, which is the GCD of 22 and 45. Okay, so that's how you may want to go about doing this problem. All right, so now the last problem is to again write a program that computes the GCD of two numbers. Okay, but here we're not going to use Euclid's algorithm in an iterative fashion, but we are instead going to use the Euclid's algorithm in a recursive fashion. Okay, so you want to write a program called gcd_rec.hmmm that implements Euclid's algorithm recursively. Okay, so here is the recursive definition of Euclid's algorithm. It says that the GCD of x and y is simply x if the value of y is 0. Okay, so that's what we call the base case of the recursion. But if y is not 0, then we are saying that GCD of x and y is simply the GCD of y and the remainder of x and y. Okay, that is if y is not equal to 0. So this is the recursive step. All right, so this is what you want to try and implement in the starter file that is called gcd_rec.hmmm. Okay, now if you open that file, you will see that it also has two parts, a main part and a function part, and I'm going to now say a few words about how you want to organize the function. Okay, so let's do that. Okay, so here I'm going to first just write that recursive definition just so we have it handy. So GCD of x and y is simply GCD of y and x mod y if y not equal to 0, and it is simply x if y equals 0. Okay. Now this is the base case, and this is the recursive step. All right. Now here again, I'm going to assume that x is in R1, y in R2, and that the GCD of x and y is in R3. Okay, the result will be placed in R3. Now the first thing that you want to do is in the main part, remember to set so in the main part set the value of R15, which is the stack pointer, to some arbitrary location. So we're going to use 100. All right, and we do this because to implement this recursive solution, we're going to have to make use of the memory. So we're going to have to store things in the memory. Okay. So remember to do this, and then in the function part, this is what you may want to try and do. Okay, so here's an outline. So you have some instruction number, so that's a placeholder. All right, and then you first you check if R2 is R2 0. Okay, so there are two answers to this question. What if it is 0? So remember that R2 contains the value y, right? So here we are checking if is y 0. Okay, so we are and if it is 0, then we are in the base case, right? So in that case, what we want to say is that the GCD of x and y is simply x, right? So what we do in this case is simply assign the value of R1 to R3, and we jump to the caller. Okay, so remember it's R14, and this is essentially the base case. Okay, so that's done. Now let's look at what you need to do if the answer to that question is a no. So then what you want to do is, this is where you want to be a little careful. So you first need to increment R15, which is the stack pointer, by 1. Okay, and then what you need to do is you store the value of R14, and that is, remember, the return address, right? You store the value of R14 at the location in memory that is given by R15. Okay, so you need to do that. And then what we want to do is, so this is the recursive step. So this is where we are trying to implement the idea that GCD of xy when y is not 0 is simply the GCD of y and x mod y. Okay, so now R1 needs to take on the value of R2. Okay, and then R2 needs to take on the value R1 mod R2. But here again, you know, based on our discussion in the previous program, you want to use a temporary register to get this done. So you want to use an intermediate register such as R4 or something to implement this. Okay, so I'll put a star here, and it's the idea that we discussed in the previous problem. Okay, so and once you do that, then you make your recursive call. Recursive call to this very function. Okay, but where does the function definition start? Well, it starts right here, so I'm going to just say a recursive call to A. Okay, and then what you need to do is you need to load the value at R15 in memory into R14. Okay, and then the last step is simply jump to the caller, which is R14. All right, so that's it. So this is what this is how you need to set up, you know, the recursive implementation of Euclid's algorithm. Okay, and once you have done this, then you should again assemble and run it. So you first assemble and turn this into gcd_rec.b, and then you run it using this command, and if your input is 54 and 24, you ought to get the result 6, and if the input is 22 and 45, you ought to get the result 1. Okay, so those are all the problems that you need to work on in this project, and then so these are the files that you will be turning in. All right, now so before you submit, you know, you just want to do certain things. All right, you first want to run this program, run tests.py, to make sure that your programs meet the input and output specification. All right, and so the way you do that is you know, you run this command on the terminal. All right, and now for problems, you can either leave it empty, in which case the script will test all of your programs. But if you want to test a specific problem, you can just list it here. So for example, if I say Python run test.py 1, 3, and 5, then the script will test the problem 1, 3, and 5. Okay, so let me quickly do a demo of that. So here I am in this folder that contains my solutions to the problems in the project. So if I say Python run tests and don't give it any input, then it simply tests all of my programs. Okay, and if everything works out properly, then you ought to see this message that says pass in green for each of your solutions. Okay, and if your program doesn't produce the right result, then you will see the message fail in red. Okay, and now if you want to test a particular problem or a particular set of problems, like for example 3 and 5, then you can just put those numbers there right next to run test.py and hit enter. So in this case, run test.py only tests those two problems. Okay, so you should always remember to run tests before you turn in your solutions, because only then you can sort of be reasonably confident that your programs meet the input and output specifications. All right. Okay, so that's that. And then the other thing that you want to remember is that the report that you write doesn't exceed 400 lines, so it shouldn't be too long. And then make sure that it doesn't contain spelling mistakes and so on. Just run it through a spell checker or something. And then make sure that it also doesn't contain lines that exceed 80 characters. All right. So you should always try and wrap your lines around by using the carriage return or the enter. Okay, so if you think that your line is too long, just make sure that you wrap them around using the enter key. All right, so the line shouldn't exceed 80 characters. Okay, so now let me quickly show you the template for writing the report. So it's right there. So let me open that. So here's a template that you should use to write your report for the project. Okay, so you want to tell me how much time you spent on this project, and then for each of the problems you want to give me a short description on how you approached each problem, any issues that you encountered, and how you solved those issues. Okay, now I just need a few lines from you on each of these problems. Okay, you don't have to say anything in tremendous detail. I just need like a paragraph or so for each problem. All right. Okay, and then in this section here, you want to tell me about the people that you received help from. Okay, so I need to know their names. I also need to know their status, meaning if they are your classmates or CS 110 grads, or the TAs or anyone else. Okay, and then I also need to know about the nature of help that you received from that person. Okay, just like in a few words. Okay, but this is very important. If you received help from someone, you need to tell me about it. Okay, all right. And then finally, in this section, feel free to give me some feedback. I would love to know if you learned anything from this project and whether or not you enjoyed doing the project. Okay, and if you have any other comments, feel free to put them here. Okay, so that's all that I had to say about this project. So I hope you guys enjoy working on it, and I hope that you get something out of it. Okay, good luck. Thank you. Bye.